So today I would like to show you how to make linear layer in Triton. Took me long to understand. I hope if you are stumbled upon this, you can find this video helpful. So Google AI, previously analyzing my video in YouTube Studio, told me to show result first and then continue the video. So I'm doing it. As you can see, I have achieved more or less stably bigger result than standard CUDA library. So my top result, I suppose, is 77 teraflops. I also done int 8 version and it peaks around 225 stops. Well, yeah, kublas sometimes can be better, but my version seems like, my Triton code seems like more stable or so, but it is not the advantage of Triton to like beat CUDA, but more like fuse the operations. So I try to explain for you how I made this. So let's start from matrix multiplication. Like basic matrix multiplication, what you do? You take row of the first and column of the second matrix. You do dot product and you get one single number that belongs here. And then you repeat this cycle over and over again to get full row. Then you go to next row, you fill next row, and so on and so forth. You probably already know this. But what if we will move to block matrix multiplication? It is actually the same, pretty much. The one important distinction is that dot product is now just matrix multiplication, or at least in Triton you do so. It is basically matrix multiplication, but in general it is still dot product. So let's assume this is dot product, and you take one row of the blocks. You usually load them separately, but I show like full, and you take one column of this and get one single block in result matrix. Why we take this approach rather than use simple numbers? It is because first we want to embrace the L2 cache reuse, and second, it is easier to transfer one block once to L2 cache and then process it, and you output, because L2 cache is far more faster than VRAM. So one important change that occurs when we do linear block instead of, by the way, it is linear block without bias. I think it is pretty straightforward how to add bias to it, but I don't want to deal with it right now because bias isn't actually helping that much. So one important change we do is to rotate the matrix, transpose the matrix. And we do this because now we can have contiguous columns, because right now they are like stored like this. And if you want to get a column, you basically do this. You like take from the very start or whatever the index of column you have. And this is way harder to load, I think. Or actually, I don't know why we need contiguous memory, because I'm not specialist that much. So let's assume it is very vital to the overall GPU loading experience. And we take this, we multiply by this, and we get again single number. And honestly, this makes far easier to index it, at least in understanding of this indexing. But we can actually optimize it further. This can be illustrated by this sort of diagram. In one case we load 90 blocks in total to shared memory and we get 9 blocks. And in second way we we load 54 blocks and get also 9 blocks. And this approach is like double the, it is like solves two problems in one solution. So it is reduces number of loads, and actually it is embraces the L2 cache reuse. I will explain why in a minute when I will show how this works. So let I show you how this works. So you take, by the way, k dimension is handled by loop in the kernel, so we shouldn't care about it very much. We actually load full row, but we compute only one block at a time. It is like looped, and we take one row from this. We get one block in result matrix. Then what we do next? We load second row. It depends on group size, how much rows we will load. We load second row and same column, and we get this block in result matrix. Then we load third block and same column, and we get this block in result matrix. And we continue this for next. We basically iterate through these three rows for every column, and we fill this entire block of rows. Because our group size is 3, we fill just 3 rows. And I actually understand that my explanation may not be as good as it should be, but actually worked and done this. It is basically shows every block that has been loaded and every result that been yielded from this. And this is like direct comparison. So in regular matrix multiplication we access 126 for 9 blocks, and in this case in matrix multiplication with Swizzling we get 54 blocks accessed and 9 blocks of result. But what is more interesting, for me at least, it was to analyze how many blocks are loaded and computed, and it is actually working very well because it reduces number of total loaded block for 9 blocks from 234 to 162. So you will have this whole whiteboard in link down in the description below if you want to investigate this more. By the way, I said 3 times because it is like literally loads 3 times for 9 blocks, and for every of this is also true. So let me explain all this code of kernel. Mostly I should explain just this part, and all of this stuff is just regular tiling matrix multiplication, because I may not said this before, but block Swizzling is actually not changing the logic of multiplication, but rather it changes the order of loading. So we just need to modify MPID and NPID, because usually in regular matrix multiplication they are just in regular matrix multiplication they are just those. So we really just changing the order in which data is loading. This part is understandable. We just want to know how much blocks we have in each dimension. This is number of PID n. Number of PID in groups. In one group. Start PID n. In original code from tutorial in Triton documentation, it named the first PID M. I found it a little bit inconvenient, at least for me. So I named this start PID M, and this is if our number of blocks in M dimension is not divisible by group size. And this is actually the case here. I mean, in this matrix multiplication. Also, I would like to explain what mindset I have usually when working with integer division and modulo operator. I like to think about modulo operator as sort of cycle or loop inside loop, but with indexes. For example, it helps to index row when you have just one index. And I like to think about this as sort of incrementing operator. When I crosses the 3, it increments by 1, and so on. It is actually helps, for example, to index a matrix, 2D matrix, if you have just one index, what we actually have in Triton. Column index, let's say we have 5 by 6, so 5 columns, 5 rows, and 6 columns. By the way, I said that it is easier to index rows with it, and I was wrong, because it is actually 4 columns and this 4 rows. As you can see, we can index the data with 2D data with one index, with actually one loop, not nested loops. This is cool, isn't it? So next part I got extremely wrong. Honestly, I'm not that confident that I understood it back then that well. So I explained what this part responds for, and I just should run this simple experiment and to know that this value will go to 0 when this entire block will be ended, and then again this, and this is not ended because we use just regular matrix multiplication. Actually, I will explain it. So it is logs PID M down to oscillating between 0, 1, 2, 3, 0, 1, 2, 3. And this part will add the starting point of this group. This is doing the same. It will go to 0 when this done, and this will increment when one column is being multiplied by every row in the loop. This means we can proceed to next column, and over again to the end of columns. We can show how it indexes by just showing indexes. So as I said before, it loads this row 3 times and it multiplies it by every of those rows and gets this column done. Then it goes again to the next, again all 3 groups for one this, and we get second column, and I suppose again this, and we have this, and then we still load those rows until we fill all row, and we proceed to the next row, or rather block of rows. So let me know in the comments what you think about this explanation, and if you find it more confusing than simplifying, also tell me about this. I will try to improve for the next time. And this is actually basic indexing of matrix in blocks. This part was actually easy to figure out, and I'm pretty sure you can do this on your own. It is actually better if you do this on your own, because you then understand better than whatever the professor or blogger like me will tell you. So actually you probably should have just create something like this and just build something like this, like I have here. This is actually how I learned. I just basically did all the GPU job, but visually. And I can see now where blocks are and how they are loaded. And actually what is also helpful, it is how you load the matrix. And you load it like this. This is basically how it fills this entire matrix. So I will actually include the footage of how I'm writing this kernel a little bit further in the video. And now I'm kinda try to tell my way to understand this. It is actually mostly described in kernel notes. What I started with is just basic matrix multiplication, and I tried to know what dimensions to use. This is actually where I discovered that in linear layers it is not basic matrix multiplication, but rather this weird, at first glance weird shape that usually is transposed. But I didn't do this because I basically can customly index it, and I just didn't care. There comes interesting part, because before this function I actually was staring at the screen for about 2 hours one day and 4 hours and in next day, and I tried to understand this by just reading the article, and it is bad thing to do actually. You want to plug and experiment with it. So I recommend you do same, not just copy the code, but rather play with it, and you will understand better. So here I explored here I explored how to index matrices in blocks. I hope it was entirely on my own, just that I have few errors that I plugged into AI, and it helped me to understand better. And then I tried to... What I did basically is I copied code from here and just printed it. It worked with my previous code because, as I said before, it just changes the ordering of how data is loading, not the actual logic. So I adapted to my variables names and it works. And this is actually, with this setup, I built this all stuff. Actually, I also played with different data types, and it was really fun. I was kinda sad because I can't use int4 because my GPU is not that new. It is 3090 by the way, and it just didn't has hardware support for int4 as far as I know. So, and this has resulted into all of this stuff. This code will it will be posted on my GitHub, and you can download it and play yourself. But I recommend you to do it yourself. Just open up editor and start doing stuff without any help from internet or AI. Just use your notebook and basic knowledge about math. The Chronicle of a Triton Kernel, composed by AI, read by me. I swore to carve the tensor in the dark, without lantern of borrowed line. No copied script should leave its silver mark upon this blank, unyielding code of mine. A linear layer simple, so they claim, an MLP in basic weight and stride, yet standing at the threshold of frame. I knew not where the hidden vectors hide. I cast PyTorch's element apart to view the raw components on the floor, and wondered why the weights by ancient art must sit transformed before the open door. Contiguous memory, the prompt replied, a subtle truth the low level had denied. I turned to tutorials seeking light to read the docs of matrix multiplication, yet standard gems were distant in my sight. While I was trapped in batch-vec transformation, my case was different, whispered my deceit. I batched array demands a unique grid. I reached to sketch the tensor in the feed, searching for graphite where the truth was hid. I wrote an index formula so grand, compounding blocks and dimensions 3 across the land. A heavy math to set the execution free. 2 hours of staring at glowing screen, I stepped away to clean the space between. Returning refreshed, I sought the treat once more, deconstructing indices, batch, row, and call. This grid was right, I argued at the door, then paused and felt the static in my soul. A cold clarity broke through the foolish strain, a bitter laugh that echoed through my room. This grand design, this fever of the brain, was standard game wrapped in unnecessary gloom. I had rewritten what was already clear, inventing monsters in an open field. A simple answer hovered tantalizingly near, yet proudly I refused to let it yield. I could have copied Triton's elegant frame, but chose the harder road to earn the name. A new day dawned. I brought the sketchpad out, determined now to trace the blocks straight down. I walked into the sun to flush our doubt, carrying a latent shape through town. How does the hardware know the interproducts bound? How the pointers meet across the scene? No AI prompts. I would wrestle ground by ground and forge the answers in my own code stream. Then came the wall. The program broke in peace. The pointer of sets twisted out of the line. Pride barred the door, refusing all release. Impostor syndrome whispering in design. If you must read the docs to understand the art, did you create or merely copy-paste the part? I broke my vow and read the writing guide, not just the syntax but prose behind, And there it stood, when math and hardware hide. A word that baffled my unseasoned mind. What is a group? I cried out to the night. No set of data bore that mystic name. Was it a tile? A thread block in the light? Or some hidden structure of GPU's game? Ah, not data at all, but order of a stream. A schedule telling execution where to thread, to maximize L2 cache within machine, and keep the memory bandwidth rich and fit. The fog cleared back, the term no longer bound, a tactical path across the tile ground. I stripped the Triton code and started small, rebuilding simple tiles in PyTorch first. An hour's work, no major errors to recall, except the validation bug that cursed. Fixed in a breath, the baseline logic stood, now facing the last boundary in the flight. Those top few lines in calculation good were PID-M and PID-N, set tiles all right. I copied down their math, retaining their trace, renamed the variable to fit my view, and printed out indices in the space to watch how execution drifted through. I watch the printed variable unspool. It sweeps a column down through group size rows, multiplies the matrix by that common tool, then to the neighboring column boundary goes. Once every column in the group is run, it drops down to the next row block below. Is this truly faster? I question what was done. Or does it drag the execution slow? I drew the grid upon a whiteboard wall, tracking loaded blocks against the tile space. Visual math responded to the call. Few were called fetches from the global memory space. The same output tiles, cached efficiency high. The sudden aha illuminated in the sky. With understanding locked, I moved the code from PyTorch testbeds into Triton's core, and I translated down the hardware road. I spotted what I had missed before. Inside my loop, I forget offsets anew at every horizontal step along the way. Redundant work, a simple fix would do. Compute the base once, let constant tries play. Just add block size k as the loop proceeds, and watch the pointer math fall into place. A clean reduction serving kernel needs, with minimal overhead across the execution space. The final test, subject the grid to strain. I fed it precision across the board. FP32 following through the line, FP16 slicing like sharp sword, BF16 with its wide dynamic range, TF32 and int8 packed in tight. The kernel held, no overflow or change, corrupted the results within my sight. It worked, not isolated, nor completely unassisted, for AI cleared the roadblock on the line, yet through frustration where the fog persisted, the mental model formed is truly mine, from tensor row to block index math aligned, from tile groups mapped to the cache efficiency known, the kernel runs, optimized and refined. A low-level victory I can call my own.